Hey guys, welcome back to part 5 of relearning machine learning. For this video, we're going to be continuing off what we covered in the last one, which was based off neural networks. In this case, we'll be looking at the cost function, and looking at some of the necessary changes to basically make what we've learned so far in terms of the cost function and backpropagation work with neural networks, which is actually quite important. From there, we'll cover a few other things. Do backpropagation, which is really important. We'll do manual gradient checks and take a basic look at how this whole process works when you actually implement it. So let's get started with the cost function. So if you, I guess, think back to a few videos ago, we covered the logistic regression cost function, which looked something like this, right? And if we adapt that to work with neural networks, well, it turns out it looks something like this here. There's a few things to watch out for. So I think the first one is the summation over k. If you remember back to the last video, keep in mind that we had, say for the classification problem, 4 different output values in that output vector. Like for example, with the motorbike, car, truck, and pedestrian one, you'd actually have to sum the error over all of those. So that summation over k takes that into account and tries to deal with that. The next thing that we should be looking out for is this regularization term. Notice how it does a huge summation over quite a few different things, and this is basically just to ensure that we're accounting for the multiple data matrices that we're going to be looking at. Something else I've written down here, which I think is, I guess, important to keep in mind, is the size of these matrices, of these theta matrices. So the number of columns in the current theta matrix corresponds to the number of neurons, if you will, in that matrix, right? And the number of rows in the current theta matrix is equal to the number of nodes in the next layer, and that's excluding the bias unit. So if we put that all together, it looks like this equation here. And what we do with this is, we'll do a partial derivative over the cost function, and we'll do something called backpropagation, which is going to look something like this here, the partial derivative of j of theta. So I've written down in my notes here that backpropagation is the neural network terminology for minimizing the cost function, similar to what we were doing with gradient descent earlier. Backpropagation really is just like gradient descent. The whole idea of backpropagation is let me see. With gradient descent, what you're doing is you're directly affecting the previous parameters. But in the case of backpropagation, you can't directly affect the previous parameters because there's multiple layers of these parameters and there's multiple sort of calculations being done. So what you need to do is you need to backpropagate the errors such that you can, do gradient descent for every single one of these weights or parameters, theta. So there's, I guess, a few steps here. Something else I've written down is that we want to minimize our cost function j using an optimal set of parameters in theta. So how do we get to this, partial derivative of the cost function with respect to each theta? Essentially what you're going to do is you're going to, do the derivative at the end, at the output layer, and then you're going to, using some linear algebra, basically move it back. And actually, when you look at the linear algebra, it's really, really easy. So I'm not gonna lie, I was hoping for a bit of a better slide here. I went through some of the slides in the course video, but I wasn't able to find a particularly good one. better explaining backpropagation and the steps there. Andrew, I think, does a relatively decent job in the video, but in terms of like a pure slide, it's not really available. I would recommend that you go and take a look at this stuff yourself. I think there's plenty of resources right now available on the internet explaining exactly how backpropagation works. Even showing you the the code implementation, which is really, really handy to see, as well as the mathematics behind it. The intuition of this sort of delta is that, I guess, the error each layer is that, you know, each layer sort of corresponds a certain amount to the total error. That is to assume that you have an error at the output, which you most probably will do. If you don't have an error at the output, then, well, something's probably gone wrong. And when you actually do the maths, you find out that the error, that is corresponding to a certain neuron, for a set example, is actually the value that you've passed through the example. So if you have, say, one neuron getting, let's say, a 3 passed through, then it turns out that when you get to the end, and you come back, the error corresponding to that particular neuron will be that 3. So after you do that backprop, there's something else that you can do to check your answer, or to check that your sort of methodology is correct, which is to do a manual gradient check. And essentially what this is doing is basically approximating the derivative. So we know that the derivative is approximating the gradient, or actually the derivative is the gradient. And how do we approximate the gradient? Well, we know that the gradient is equal to, say, the rise over run for a particular equation. So if we go to the next slide here, basically if you like slightly perturb your theta, then you can do a manual calculation of this gradient, and it's particularly important that you do this over a plus and a minus. So that is to say, you don't just go theta plus e, but you do both theta plus e and theta minus e, as this gives you a more accurate result. What else have I written down in my notes here? Backpropagation is very prone to error. To ensure that our backpropagation worked as intended, we can approximate the derivative of our cost function with this, where a small value of e, such as 10 to the negative 4, ensures that the math works out properly. And that is actually quite important as well. You don't want to be picking a large e, because if you do, then you're probably going to miss out on quite a bit of the nuance of this curve. So you should be picking something quite small. I think there's some code that comes up in the following slides. Maybe here. I think I've written down, this code gives you a grad approximate vector, which you can then use to check against your delta vector. And this can be done once. So normally these days you don't actually do this so much. Previously, if you were actually coding like the gradient descent and backpropagation by hand, it would make sense to. But now with things like TensorFlow and PyTorch, your library handles that sort of functionality for you, and you know that the gradient calculation from TensorFlow is going to be accurate. Something else that I think Andrew's covered this week is random initialization. Come on. Random initialization, here we go.
All the pieces idea I need to share with you, which is the idea.
And the idea behind random initialization is that you can't be initializing your weights to 0, because if you initialize your weights to 0, um, then essentially what's going to happen is you're going to be multiplying by 0 and you're never going to start learning. So what you do is you actually initialize all your weights to be random values in a certain range. This is actually quite good because it sort of in effect allows your model to learn uh, without a set starting point. It allows your model to learn all sorts of different patterns, all sorts of random patterns. And in a way, this is sort of what makes machine learning work as well. Actually, another reason for that, actually, I guess, kind of incorrect going through the video again, but if you set it to 0, your gradient descent, it might, like, sort of figure out a way around it, but another reason why you can't be setting it to 0 is because, if you do so, if you set your weights to be the same value, then you might end up in a situation where you develop your parameters in lockstep. And that's because, like, say for, like the same value, like say this bias one here, A1 is going to be equal to A2, the derivative is going to be the exact same. And so as a result, your parameters like after backprop and gradient descent will end up being developed in a similar vein. So if we put everything we've learned together, this is sort of what you do when you start a machine learning I won't say project, but if you start training a neural network, if you've decided that you want to train a neural network, this is what you're going to do. The first thing that you're going to do is you're going to sort of figure out a neural network architecture. Now you could pick this, or you could just try to figure it out. The last time I really did this was probably 4 years ago now, possibly 5. And at the time, picking out your neural network architecture was really more of an art than a science. You'd sort of like take a rough guess at what would work best, and maybe you could do a bit of optimization here and there. But ultimately, you use your intuition and you use, what other people are using as well, to try figure out what the best architecture was for your problem. So that looks something like this here. You could decide on the number of layers, you could decide on the number of units per layer, and as you get to more like complex neural networks, you'll decide on other features, not necessarily features, sorry, but maybe other methodologies and other special techniques as well, which you can use. So I've written down here that as default, normally you'll have at least one hidden layer, and then you might have a large number of hidden units. So then part 2 is going to be, training this network. So what you're going to do is you're going to randomly initialize your weights, so you avoid that symmetry problem that we talked about earlier. You're going to do forward prop, so for your data set, you're going to pass it through the network. And you're going to get the error, you're going to do the cost function, and then you're going to do backprop to get the partial derivatives of that cost function value with respect to each of the thetas, and then you're going to update the parameters corresponding to that error. And you're going to keep repeating this. So for every single data point you have, you're going to do forward prop and back prop and forward prop and back prop, doing this sort of gradient descent until you get to a place where you're sort of happy with. And honestly, that's it really. Like what you'll do normally is you'll look at the loss graph or the cost graph, and based on the graph you'll decide when to stop training your model. Normally it's when it sort of stops improving, and you can see that the cost between your training and your test sets are roughly equal. Or sorry, the loss is getting to be close to equal, but not equal. That's important. because if it is equal, then you probably have something wrong with your model. I've written down here a fifth step. You can use gradient checking to compare this partial derivatives of backprop and do a numerical estimate. I think is that written down here. Yep. And then I guess as the final step, Andrew has that number 6, which is basically just to go through with gradient descent. Minimize j of theta as a function of the parameters theta. Cool. So that was it for this week's content. To be honest with you, it took up much less time than I expected. I think the reason for that is I didn't really go into the maths or go through the examples that Andrew went through for back propagation, but you might find that that's quite important for you to do to actually get a really good understanding of this. But to be honest with you, like you don't really need to know it that much these days. Like you just need to know what happens because realistically, you're not going to be going in and doing coding that up yourself. And more so, depending on the library you use, it's pretty well established how this particular process looks. But I hope you found this week's content interesting. I hope you found this video, I guess, stimulating to some extent. Next week, we're going to be covering a few things, and actually, next week's content is where my notes end. There's, I think, a week or two after that, but I guess I was just lazy and I stopped taking notes. But I'll see if I can cover that stuff as well. But we'll be looking at things like error handling, bias and variance. It's what else? We'll be looking at the learning curves, which is what I was talking about with the error and loss. Model complexity, and maybe some issues around data and how to assess your model as well. Sweet. So that's it for this video. I hope you enjoyed. I guess I'll catch you guys in the next one. See ya.